So, let us discuss one numerical on energy of photon, right. A 100-watt bulb emits a monochromatic light of wavelength 400 nanometer. Then calculate number of photons emitted per second. See what is given here, we are given with power. Power equals to 100 watt, right. We have energy is equals to power into time. Power, so it is 100 watt into second. 100 watt second is joule, energy is 100 joules. Now this 100 joules contains how many photons? That is what we have to find. Now this 100 joules has how many photons? This is the point we need to calculate. Now let us see this here. We have E is equals to hc by lambda, energy of one photon. Energy of one photon with this wavelength, it is 6.625 into 10 power minus 34 joule second into velocity of light 3 into 10 power 8 meters per second by lambda value is given as 400 into 10 power minus 9 meter. 1 nanometer is 10 power minus 9 meters. Now on simplification, 6.625 into 3, 19.8, nearly 20, 20 by 4 means nearly 5. As it is slightly less, it will be 4.9. 4.9, okay, 97 something you take into. So on simplification, this will be 25, minus 25 and 8, minus 25 and 8. So it will be minus 34 joule second, and this is minus 9. Right, on simplification it will be 10 power minus 19 joules. 10 power minus 19 joules. Now this is energy of one photon. When 4.97 into 10 power minus 19 joules is of one photon, then the given 100 watt bulb whose energy is 100 joules is of how many photons? 100 joules is of how many photons? So how do you calculate crisscross method? So number of photons equals to 100 by 4.97 into 10 power minus 19 joules. It is almost 100 by 5. 100 by 5 is 20. As denominator is lesser, total value will be slightly vary, slightly 5 2's, right. For net value will be something 2 into 10 power 20 joules. 2 into 10 power 20 joules. 20 into 10 power minus 19, right. Approximately 2 into 20, it is number of photons, number of joules is cancelled per second. So many photons per second. See, we should be perfect in the calculation part. 20 into 10 power, yes, correct. Now this is one numerical from energy of photon. This is another numerical on photons. Calculate energy of 1 mole of photons of radiation whose frequency is something. We have E equals to h nu, that equals to 6.625 into 10 power minus 34 joule second into frequency is 5 into 10 power 14 per second. So on simplification it will be 33.13 into 10 power, how much it is 10 power minus 20 joules. This is energy of a photon, energy of one photon. Now the question is to calculate energy of 1 mole of photon. Therefore, energy of 1 mole of photon is equals to Avogadro number into energy of 1 photon. Avogadro number into energy of 1 photon, that is 6.023 into 10 power 23 into 33.13 into 10 power minus 20 joules. 33.13 into 10 power minus 20 joules. Right. Now here on multiplying these two values, energy of 1 mole of photon approximately it will be nearly 218 and 19, 199.5. 199.5, right. So you should multiply this one into 10 power 3 joules. 10 power 3 joules means 199.5 kilojoules, right. This is one numerical from photoelectric effect and or energy of photon. So this is a question from photoelectric effect directly. The threshold frequency nu naught for a metal is given 7 into 10 power 14 second inverse. Calculate the kinetic energy of the electron ejected or emitted when a radiation of frequency, some frequency hits the metal. Okay, this is the frequency of the radiation that is falling on the metal screen, and this is threshold frequency, and we are asked to find out kinetic energy. Just now we studied h nu minus h nu naught is equals to kinetic energy. Kinetic energy is the difference between energy of the incident light and the threshold energy. Just in the same session we studied. So, h into nu minus nu naught is equals to kinetic energy. So, kinetic energy equals to 6.625 into 10 power minus 34 joule second into what is frequency of the incident light, 10 power 15. It is minus what is the nu naught threshold frequency, 7 into 10 power 14 second inverse, right. Second inverse is cancelled. So, that will be, that can be taken as 6.625 into 10 power minus 34. This is nothing but 10 into 10 power 14 minus 7 into 10 power 14. We have to simplify that. 10 minus 7, 10 power 14 is common, 3. 6.625 into 10 power minus 34 into 3 into 10 power 14 joules. On simplification, 6.625 into 3 is 19.8. 19.8 into, on cancellation, 10 power minus 20 joules. So, this is the kinetic energy of the ejected electron. Now, let us discuss the topic atomic spectrum. Before discussing, we should discuss some important point, we should know some important point about speed of light. Speed of light depends on the medium through which it passes. Speed of light depends on the medium through which it passes. Light beam, when a beam of white light is passed through different media, it gets deviated or changes its path. It gets deviated or changes its path while moving from one medium to another medium. When a beam of white light is allowed to pass through a prism, when a beam of white light is allowed to pass through a prism, it was noticed that violet color of low wavelength 3800 angstroms getting more deviated than red color which is of higher wavelength. See, when a beam of white light is allowed to pass through a prism, it was analyzed through a prism and gets spread out and gets dispersed into different colors, during which they noticed that see, violet light which is of lower wavelength is observed as getting more deviated than red light which is of higher wavelength. And if this is the path, actual path of this beam of white light, see, you can see the deviation now. This is of more angle of deviation when compared with the red light. Now, since ordinary light consists of waves with all wavelengths, since ordinary light consists of waves with all wavelengths coming under visible region, a ray of white light is spreading out or dispersing into a series of colored bands called as spectrum. So, when those series of light which is dispersed is allowed to fall in a photographic film or a plate, then the spectrum can be noticed. So, now what is the definition of spectrum? What is the basic definition of spectrum? The impression produced on a photographic film, I am repeating, impression produced on a photographic film by a series of radiation, impression produced on a photographic film by a series of radiation dispersed out from a prism after getting analyzed. See, once again, let us go through the definition. Impression produced on a photographic film by a series of radiation analyzed through a prism. Impression produced on a photographic film by a series of radiation generated after analyzing through a prism. Okay. So, this is the basic definition of spectrum. Now, this is all noticed for frequencies 7.5 into 10 power 14 hertz to 4 into 10 power 14 hertz. Such series of frequencies with continuous colors, violet to indigo, indigo to blue, green, yellow, orange, red, was termed as a continuous spectrum. What is the termed as? Continuous spectrum. This is all noticed for visible region. See, we discussed whatever whatever we discussed it till now, it belongs to visible region, which is a small part of electromagnetic radiation. When just for visible region these many spectral lines or dispersed spectral lines are noticed, then when all electromagnetic radiation is starting, when it starts interacting with the medium, definitely what will happen? Atoms and molecules will start absorbing energy, jumps to excited state. As they are unstable in the excited state, again they will try to come back to their normal state or low energy state. While coming back, whatever the energy released out, it will be given out in the form of electromagnetic spectrum. So that's the complete definition of electromagnetic spectrum. Now see, so when it comes to the next topic, spectrum, types of spectrum. Spectrum is basically of two types. One is emission, other one is absorption. Emission spectrum means it is spectrum of radiation that is emitted by a substance. It's not finished. Spectrum of radiation that is emitted by a substance which has already absorbed energy, Spectrum of radiation emitted by a substance that has absorbed energy means previously it has absorbed energy and shows excitation, and while de-excitation, whatever the energy emitted out, that spectrum of that emitted radiation is called as emission spectrum. And when it comes to absorption spectrum, it is spectrum of radiation transmitted through a substance. Suppose this is a substance, and a white light, beam of white light is passed through this, for example. See, it has complete brightness. Have you noticed? This is completely bright. Means every brightness, this brightness corresponds to different wavelengths, obviously. Now what happens? This substance is absorbing certain wavelengths of this radiation. Certain parts of wavelengths were getting absorbed by this substance, and the rest unabsorbed were released out. See? Now the radiation that is transmitted out of the substance has some gaps, dark gaps. Have you noticed? These gaps corresponds to the wavelengths absorbed by the substance. These gaps corresponds to wavelengths of the radiation absorbed by the substance. Such a spectrum is called as absorption spectrum. Spectrum of radiation transmitted through a substance after absorbing regions of certain wavelengths is called as absorption spectrum. We can say it is just a photographic negative of emission spectrum, like how emission spectrum contains sharp well-defined lines or bands on a dark background. See, actually photographic film is dark in color, right? Now when during emission spectrum, suppose when a light beam is emitted out, that gives a sharp well-defined line in this way. Suppose certain emissions takes place at the same time, all those emitted radiation will form a group of closely spaced lines. See, group of closely spaced lines in this way called as bands. Group of closely spaced lines called as what? Bands. Now once again, emission spectrum contains sharp well-defined lines or bands on dark background like this, whereas absorption spectrum contains dark lines or dark gaps on a bright background. These dark lines or gaps corresponds to the wavelengths absorbed by the substance. This is the basic difference between emission and absorption, and in both the cases we have another classification, that is line spectrum and band spectrum. Presently we are discussing about line and band spectrum belongs to emission spectrum. Emission spectrum again contains two types, line spectrum and band spectrum. Line spectrum contains sharp well-defined lines in this way, sharp well-defined lines on dark background, whereas band spectrum contains a group of closely spaced lines on dark background. Okay, if it is emission spectrum, if it is a classification under emission spectrum on dark background, if it is a classification under absorption spectrum, what will be the definition? Now you can easily assess. Sharp well-defined dark lines on bright background, group of closely spaced dark lines on bright background. That will be the definition, they will be the definition for the classification under absorption spectrum. This is under emission spectrum. If it is absorption spectrum, how to define? Sharp, well defined dark lines on bright background for line spectrum, group of closely spaced dark lines on bright background for band spectrum. So, this classification is there for both emission as well as absorption spectrum. Then line spectrum is given by atoms, whereas band spectrum is given by molecules, and that is why line spectrum is also called as atomic spectra and band spectrum is also called as molecular spectra. And here the important point to be noticed is each and every element has its own spectrum, which can be used for its identification. Like in one way, this spectrum analysis of this both emission and absorption spectrum, study of this both emission and emission spectrum, absorption spectrum is called as spectroscopy. Spectrographic analysis is of lot of importance nowadays. It is similar to the fingerprints of this one people. See, it is just like fingerprints of a person. How a fingerprint helps in identifying a person, just like in the study of atoms and molecules, the spectra will help us. Now, let us discuss about postulates of Bohr's atomic model. Postulates of Bohr's atomic model. Niels Bohr slightly modified Rutherford's atomic model and had given some postulates according to which electrons revolve around the nucleus in certain closed circular paths called as orbits. Certain closed circular paths called as orbits, like this. See, first closed circular path, next third, fourth, fifth. There are so many certain closed circular paths. In Rutherford's model, what they had given? They had given simply electrons revolve around the nucleus just like planets revolve around the sun in this way. Okay, but Niels Bohr had given circular orbits, fixed circular orbits concept. First point is electrons revolve around the nucleus in certain closed circular paths called as orbits. These orbits are numbered as 1, 2, 3, 4 so on, or KLM and so on. These orbits are numbered as 1, 2, 3, 4 or designated as KLM and so on. See, this 1, 2, 3, 4 numbers were later given as a principal quantum numbers. These numbers were also given as principal quantum numbers. And as each orbit is associated with a particular amount of energy, as each orbit is associated with a definite amount of energy, these orbits are also called as energy levels. These orbits are also called as energy levels, or also called as shells, first shell, second shell, third shell, likewise K shell, L shell, M shell, so on. As long as an electron revolves around the nucleus in a particular orbit, as long as electron revolves around the nucleus in a given orbit, it neither loses energy nor gains energy. Means it is stationary, these orbits are stationary. Okay, as long as an electron revolves around the nucleus in a given orbit, electron neither loses energy nor gains energy, but its energy remains constant. Means it is said to be revolving in a stationary orbit. Now, when it comes to these particular orbits, you can notice with increase in distance from the nucleus. See, this is the first orbit at some distance, second orbit is at more distance, third is at still more, very high. Like this, these orbits are at some particular distances. With increase in distance from the nucleus, energy associated with the orbit is also increasing. Have you noticed? Energy associated with the orbit increases. Next point is, as long as an electron revolves in a given orbit, it neither loses energy nor gain energy, but it remains constant. To jump from low energy orbit to high energy orbit, it has to absorb energy. To jump from a low energy orbit to high energy orbit, it has to absorb the required difference of energy. Similarly, to jump from high energy orbit to low energy orbit, electron has to release the energy. So, transition of electron takes place either by absorption or by emission of energies. Thus, energy difference between successive energy levels. Energy difference, see, just now we discussed, transition of electrons takes place either by absorption of energy or emission of energy in terms of quanta or photons. This energy difference between successive levels is given as En2 minus En1 is equal to h nu. N2 is some high level, N1 is some low level. This that is energy difference is given as hc by lambda. This emission or absorption of energy takes place either in terms of one photon or a whole number multiple of it, either in terms of one quanta or the whole number multiple of it, means 1 h nu, 2 h nu, 3 h nu, so on. This point was taken from Max Planck's quantum theory. Okay, actually this point was already specified by Max Planck. And when around the nucleus, when those many orbits are possible, like this, not only this, between these two also another path is possible. Infinite number of orbits are possible around nucleus. But then electron revolves in which particular orbit? When these many orbits are possible, practically electron revolves in which orbit? It revolves in such an orbit where its angular momentum is quantized. Means it revolves in such an orbit where its angular momentum is an integral multiple of h by 2 pi. This was another experimentally proved point where its integral later, it was proved later. This quantization of angular momentum was proposed by Niels Bohr. Later it was proved after de Broglie's hypothesis. Okay, electron revolves in such an orbit where its angular momentum is an integral multiple of h by 2 pi. MVR, angular momentum MVR, is equals to nh by 2 pi. This phenomena is termed as quantization of angular momentum. Thus, Niels Bohr also explained about the radius of these stationary orbits. For example, he had given an expression, radius of nth orbit, n may be 1, 2, 3 principal quantum number, which is given as radius of nth orbit can be expressed as a naught into n square, where a naught stands for radius of first orbit of hydrogen, first Bohr's orbit, or radius of first orbit of hydrogen, whose value was observed as 0.529 angstroms. 0.529 angstroms, and we should remember this conversion. 1 nanometer is equal to 10 angstroms. 1 nanometer is equal to 10 angstroms, and 1 angstrom equals to 100 picometers. So 1 angstrom equal to 100 picometers. If you substitute that, it becomes 52.9 picometers. So once again, radius of these stationary orbits around the nucleus of hydrogen, it was expressed as Rn equals to a naught into n square, where a naught stands for radius of first orbit, whose value was noticed as 0.529 in angstroms or 52.9 picometers. Similarly, energy of electron in nth orbit, energy of electron in a stationary orbit, nth stationary orbit, can be was expressed as En equals to minus 2.18 into 10 power minus 18 by n square joules. Okay, so energy of first orbit in hydrogen, these are all for hydrogen. Earlier he expressed. Basically, Bohr's atomic theory was given only for one electron species. The first one electron species means it may be an atom or ion. The first one electron species possible is hydrogen. So energy of electron in first Bohr orbit of hydrogen atom is, substitute n with 1, minus 2.18 into 10 power minus 18 by 1 square joules. Energy of second orbit equal to minus 2.18 into 10 power minus 18 by 2 square joule. Okay, which is given as minus 0.545 into 10 power minus 18 joules. We can calculate energy of the successive levels using this relation. Okay, this is about radius and energy expression for hydrogen. When it comes to the other single electron species, as Bohr's theory was proposed only for single electron species like hydrogen, helium plus, Li2 plus and Be3 plus, etc. On applying the same relations for other single electron species, general expressions were given as radius of nth orbit in a single electron species or hydrogen like species equals to 0.529 into n square by z, where z is atomic number of that particular species. Suppose hydrogen is the one electron species, atomic number is 1. Helium plus is the one electron species, atomic number is 2. Lithium 2 plus, one electron species, but its atomic number is 3. Likewise, beryllium 3 plus, atomic number is 4. And in picometers also, this is in picometers. radius of nth orbit in a hydrogen like species or a 1 electron species can be given as 52.9 by Z into n square picometers. Similarly, on generalizing this energy expression also, energy of electron in nth stationary orbit in a hydrogen like species is given as minus 2.18 into 10 power minus 18 Z square by n square, where Z is atomic number of hydrogen like species. Atomic number of hydrogen like species. Now, you may get a doubt, why there is a negative sign before this expression? Why energy of electron is given in a stationary orbit is given with a negative sign? Actually, when electron is moving, just now in the discussed, when electron is moving around the nucleus, when electron is moving around the nucleus in certain closed circular paths, n value ranges from 1, 2, 3, 4 so on, 1, 2, 3, 4 so on, right? You see, this is nucleus. As electron moves away from the nucleus in this way, at one moment it moves out of influence of the nucleus. At one moment electron moves out of influence of the nucleus, where its energy is said to be 0. Where its energy is said to be 0 means it is said to be ionized hydrogen. It is said to be ionized hydrogen. Same way, when the same electron, when this is electron is said to be in n is equal to infinity level. Now, when the same electron was attracted by the nucleus, it comes to the orbit which is under the influence of nucleus, where its energy is said to be lowered. Its energy is said to be lowered, indicating this a negative sign is given. As a freed electron when attracted by nucleus is lowering its energy, to specify that decrease in energy, a negative sign is given when it is in nth stationary orbit around the nucleus. Using these postulates, Niels Bohr had explained even hydrogen spectrum also. Actually, we have to discuss about hydrogen spectrum slightly before Bohr's theory. Again, the same points I to discuss. That's why I am discussing this after, along with the Bohr's explanation. Like actually, when hydrogen gas is subjected to silent electric discharge, when hydrogen gas is subjected to silent electric discharge in a discharge tube, H2 molecule dissociates into corresponding hydrogen atoms, and the electrons in each hydrogen atom absorb energy, different forms of available energy, and shows excitation. And as they are unstable in excited state, they will come back to their ground state. This coming back is called as a de-excitation. What is that called as? De-excitation. This de-excitation may takes place either in a single step or in multiple steps. Like electron from the ground state of hydrogen, first energy state of hydrogen, jumped to 7th energy state during excitation. Now, from 7th state, it may directly come back to the first level. It may directly come back to the first level. Instead, it may come to 6th, and from 6th it may come to 1st, or it may jump to 5th orbit, and from 5 it may come to first level. Like that, this transition takes place in different ways, as a result of which different large number of spectral lines can be noticed. These spectral lines, collection of these spectral lines formed when electron jumps from any high level to first level comes under ultraviolet region. Spectral lines formed when electron jumps from any high level to second level comes under visible region. Similarly, electron jumps from any high level to third level comes under near IR, fourth level means IR, fifth level means far IR, etc. Among these different series, first observation was given by Balmer in visible region. Okay, Balmer was the one who first noticed these spectral lines under visible region, and he also had given a relation for wave number of these spectral lines in visible region. Initially, he had given this relation for visible region, wave spectral lines in visible region, bearing a relation nu bar equals to 109677.8, nu bar equals to 109677.8 into 1 by 2 square minus 1 by n square. You might have noticed here this 2 corresponds to second level, means visible region lines, when visible region lines will be formed when electron jumps from any high level to second level. Electron won't stay here, again second to first it happens, second to first it will jump. But those spectral lines, whenever electron transition is from high level to second level, comes under visible region. So, wave number of these visible regions was expressed by Balmer using this relation 109677.8, a constant, into 1 by 2 square, that is the least energy level in visible region, that is the least energy level in spectral lines of visible region, and highest energy level means highest energy level starts with a 3. Minimum high energy level possible to give a spectral line in visible region is 3, 4, 5, 6, 7, that is what given. So, least energy level is 2 for Balmer series, visible region as it was discovered by Balmer, Balmer series or visible region it was called as 2 is the low energy state, and n starts from, means high energy state starts from 3, 4, 5, so on. Later Rydberg and in association with Rydberg in association with Ridge had generalized this above expression for all regions means Lyman series, ultraviolet region, visible region, near IR, far IR, okay, and other higher wavelength regions also, Humphrey series, like that. And that expression was given as nu bar equal to 109677.8 into 1 by n square minus 1 by n1 square minus 1 by n2 square, where n1 is the low level. For example, when n1 is 1, n2 possible is 2, 3, 4, so on, and such a series comes under Lyman series after the discoverer, actually belongs to UV, ultraviolet region. Whenever n1 is 2 and n2 is 3, 4, 5, so on, the series comes under visible region, which was first observed by Balmer. In this way, n1 is 1, 2, 3, 4, so on, n2 is n1 plus 1, n2 plus n1 plus 1, n1 plus 2, n1 plus 3, so on. Understood? This is how we can express the wavelength of spectral lines, different spectral lines formed in this hydrogen spectrum.